Yeah, so sequences are basically nothing else than tables. Yeah, so we again take the rows as the observations, but now the order of the columns are the values of these sequences, and the columns have a sequential order. So the order of the columns are now important. They reveal the sequential nature of our observations. And of course, we want to make use of this more richer representation now. Yeah, so the representation is more or less the same, but it has more information now because the order of the values of the row of the column, are now important, or give us more information, reveal this this sequential nature. Yeah? So if we want to mine for patterns or learn some patterns out of these kind of data, well, what do we have to do? Well, if you do distance-based mining, of course, somehow, well, we learned that similarity, distance is the key. So we somehow have to come up with appropriate distance functions, the distance measures or similarity measures that account for this sequential nature of these of the columns. Yeah? And of course, that is very specific to the specific patterns that we want to get. So here, as you see, we'll get to know 3 different similarity models for sequence data, which are the most common used for sequence data. But of course, you have to think about what kind of patterns do you get when you apply those distance measures. Yeah? So if you apply different distance measures, like the Hamming distance, the edit distance, or the longest common subsequence, you get different patterns, and you have to think about, is that exactly what you want? If that's not, if you want to have different patterns, then of course you have to consider other variants of similarity measures or distance measures other than those that we are talking about here. Yeah? And there are many, many more. This is just the tip of the iceberg, so to say, but this somehow should give you a kind of idea how to deal with this sequential nature of the data. Okay, so let's start first of all with some first words, so to say. Yeah, so very often distance-based models are employed, as we just said. Okay, of course we could also apply neural networks, especially recurrent neural networks or one-dimensional convolutional neural networks perform extremely good in many times or in many cases for sequence data. But as we discussed it in the introduction, there are many applications where you don't want to rely on, or you cannot rely on neural networks. So there is still very often the case for the traditional distance-based methods or handcrafted feature-based data mining or machine learning methods. Yeah? So the most important question, what we just said, is how to actually account for this sequential nature of the data, how to account for the fact that the order, the sequence of columns now gives you more information, has some kind of semantics. Yeah? Of course, what we also already said, we can use different similarity models that do the job, and here is the overview of the 3 that we want to present to you. So the first one is the very simple approach, which is called the Hamming distance. Is very similar to the Euclidean distance on vector data, and yeah, well, we just align the sequences as they are. Yeah, so we also talk about, in that case, of a naive alignment of the sequences. The second one which we want to introduce to you is the edit distance. Here, that is a so-called transformation-based approach that somehow measures the costs that are required to edit or to transform one sequence into another one. Yeah, using different edit operations. We'll have a look, of course, on that later on. The byproduct of this one here is that it reveals also an optimal alignment of the sequence. So not each row from each column from one row needs to be mapped to exactly the same column from the next row, from the next sequence, but we can have a kind of flexible alignment of the sequences. And the third one here is the longest common subsequence. That is a similarity measure actually. So the first two are distance measures. This is a similarity measure, and that utilizes a third common basis sequence. So it tries to determine what is the common basis sequence of the two sequences that I want to compare. And it is a kind of variant to the edit distance, but we will see that later on when we go into the details. So we'll start with the Hamming distance. And as we said before, the Hamming distance somehow imitates the Euclidean distance. So it just counts the number of positions with different elements. Yeah? So it accounts somehow for the fact that the objects are sequences of some symbols, but in a very, very coarse sense, or very naive sense maybe. Yeah? So the formalization is very, very simple. We have two sequences, Q and S, with the particular values, Q1 to Qn or S1 to Sn. The most important point is in the basic form that these two sequences need to have the same length. You see, both have length n. Yeah, so both have an index set of size n. And then if we have that, we can define the Hamming distance by this formula here. And if you look at this formula here, we just sum up these delta values over all the different positions here. Yeah? And these delta values can be computed very very easily. Well, if the values at the particular position are equal, are similar, are identical, yeah? Then the distance is 0. Otherwise it's 1. Yeah? So that is especially easy for categorical sequences, of course. Yeah? So if we have non-categorical sequences, of course we could use somehow square distance or stuff like that here instead of 1. Yeah? But if we just have categorical distances, of course we just can distinguish between 0 and 1. Yeah? So if it's similar, identical in that case, the distance is 0. If it's not similar, if it's not identical, then the distance is 1. And we just sum up, in that case, all the positions with different elements, obviously. Yeah? So the sum gives you the number of elements or the number of positions, sorry, which with different elements in Q and S, obviously. Yeah? So the workaround for sequences that have not the same length, well, if it's only applicable to this scenario, it's a very, very limiting scenario, of course. So there's a workaround for sequences that have different length. In that case, we just use typically artificial symbols as a fill-up, and we see that on the example here on the next slide. So here's an example where we want to compute the Hamming distance between this sequence here, which is the word 3, and this sequence here, which is the word tree. Yeah, so we have two sequences over an alphabet of characters in that case. Well, what does the Hamming distance do? Well, first of all, the two sequences have different length. So what we introduce for the smaller one or the shorter one, we introduce these artificial symbols here at the end, artificial elements from the domain here at the end, which should give you a mismatch, of course, in that case. So yeah, and then you can compute the Hamming distance. So you just see or look at each individual position and count a 0. Well, a 0 if it's identical, and a 1 if it's not identical. So here T and T matches, obviously. H and R does not match, so we have at least a 1 here, a 0 here, a 1 here. Then R and E does not match, do not match too, so another 1 here. E and E match, so a 0 here, and E and the artificial element also is a mismatch. So we have 3 mismatches, so the Hamming distance is 3 in that case. Yeah? So you see it's very strict matching, very similar to the Euclidean distance, and yeah, similar subsequences like R, E, E it's appearing in both sequences here, but on a different position, and we cannot consider this or cannot account for these similar subsequences, which is the case here, but we cannot account for that with the Hamming distance, because we are not allowed to align the sequences in a different way than just aligning them one by one as they come. Yeah. And in that case, yeah, the subsequences or the sequences are not aligned appropriately. So in that case, it would be better to use this fill up here at the second, or especially at the second point. Yeah. So if we use the fill up here at the second point, we would have a perfect matching. Just this one here would be a mismatch. In that case, the Hamming distance would be 1. Yeah. But we cannot do that because typically these fill-ups for sequences of different length are placed at the end of the shortest sequence as it is done here. Yeah? And it's just for performance reasons, because otherwise we need to determine what is the perfect way, or what is the perfect location for those fill-ups, and that would end up in determining the best alignment, and that is not what the Hamming distance wants to do. That is actually what the edit distance wants to do, and that is of course next. Yeah, but sorry, this way. Yeah. First of all, before we talk about the edit distance, we just have other examples here for these misaligned sequences. So here we have Türschloss, for example, and Torschuss. Oh no, once again some soccer thing, but anyway. And you see again here that we have a Hamming distance here between Türschloss and Torschuss of 4, and the Hamming distance between Türschloss and Abschuss is 10. And if we have a closer look here, well, we have here the matching of this SCH and SS down here, and the same here. Well, here we have another matching here and here, but it's just we cannot align those similar subsequences, which is better here, but we cannot align these similar subsequences of Abschuss here with Türschloss, which is so the alignment here is better than here, even though if we do the proper alignment, or if we could do the proper alignment here, the Hamming distance of course would be much smaller, but here now, since we cannot do that, we have a very high Hamming distance. Yeah, so the similarity of the subsequences Schloss and Schuss are not considered by the alignment which is done by the Hamming distance. Yeah, and that brings us to the idea that we not use these fill-ups here at the end, but we can use fill-ups somewhere in between, so that the distance is actually minimized. And that is the idea of the edit distance, which is coming up next.